Hello, everyone. I am going to discuss and kind of dive into severe weather here. As we're approaching severe weather season, I felt like it's a good time to just introduce some different topics, some different forecasting tools we use, and different sorts of just different sorts of ways we can kind of forecast severe weather just in general. So it's a very interesting process. It's a very complicated process. I'll be just briefly touching some of these things, maybe not really explaining them too well. I'll try my best. Um, of course, if you have questions, leave them in the comments, but I'll try to explain them as best as I can. This will be two parts. Um, the severe weather PowerPoint will be two parts, so hopefully it's not too much. Hopefully I can explain stuff decently well. Um, and if you are curious in anything, definitely look it up on your own, or I can you can ask me in the comments, and I can leave some good links for whatever question you're asking. If especially if I can't explain it well. Anyways, so oh, let's get started. So there are three main ingredients we need for severe weather. We need lift and moisture, instability, and wind shear. For lift and moisture, we get this we get this moisture from the jet streams and our jet streaks. We get the lift from this positive vorticity vection (PVA), which we'll discuss. But we also get it from surface fronts like cold fronts, dry lines, which are more common in like Texas, Kansas, Oklahoma, and that sort of part of the country, and then boundaries. And then, like I said, instability and wind shear, which we'll go into very shortly. First, I just want to discuss the importance of a jet streak. And this might look confusing, but what we like to do is we like to separate these jet streaks into four quadrants or exit or entrance regions, which you'll see in the next picture. But really, we like to separate into four quadrants, and um, these jet streaks have different um, different sort of aspects to them. So, like, there's a divergence on the bottom left and on the top right, and then convergence. You need divergence to um, make air rise. You need it for low pressure development and just storm development in general. So if you have a high area of um, if you have a high area of an enhanced jet streak, you're going to have higher divergence, and you're going to cause whatever low pressure or whatever system or energy to be enhanced, because that air is going to be forced to rise. So it's important when we're forecasting for severe weather and just in general is to look at these jet streaks and where they're at, where they're placed, how the trough is located, how it's oriented, which we'll also get into. This is all very important for forecasting. This is an example of a jet streak. Um, you can see the left and right entrance and left and right exit. Just kind of ignore that. That's the same sort of idea as the four quadrants of the convergence and divergence. It's the same idea. It's just kind of named differently. Um, but we can see our jet stream come where these arrows are pointing, the left and right entrance. You can kind of see it going out of the picture. And you see our jet streak here, and there seems to be another one right here. Really, this whole thing could be classified as a jet streak because it's very blurry, but we have the heightened winds, the pinks and the reds. That's high, that's stronger winds, and you see the overall jet stream kind of really fizzles out once it hits Europe here. But this is the good example of a jet streak here. And again, this picture here and this picture here I got from the links above. They are not mine. So, kind of just briefly discuss this. Talk about pressure levels, different levels of our atmosphere. First, we'll talk about the upper atmosphere. During the summer, we look at 200 millibar, fall and spring 250, and then the winter 300. This is usually around 33 to 43,000 feet in the atmosphere. We mainly use these maps, these pressure level maps, to identify long wave patterns, jet streams, and jet streaks. And long wave patterns are essentially just troughs and ridges. Um, and then, of course, millibar is just it's an air pressure measurement. And then why do we use the millibars for different seasons? Well, the jet stream is placed differently throughout the seasons. So during the winter, it's closer to the surface. Now it's still up high in the atmosphere. It's a little bit closer, and we can use the 300 millibar to really um, get a better, more accurate idea. But in the summer, where that jet stream is lifted up, raised higher up in our atmosphere, just slightly higher than the winter, we use the 200 millibar because that gives us the most accurate data and imagery. So our next part of the atmosphere is our middle atmosphere. This is around the 500 millibar layer. As we go closer to the surface, our millibar number goes up. So um, kind of just something to remember. But this is around 18,000 feet, and we use the this layer to really identify our PVA and NVA. Well, what is that? That's positive vorticity evection and negative vorticity evection. Okay, well, what is that? So positive vorticity evection is just higher vorticity values being brought into an area with lower vorticity values. It's being advected, it's being moved into an area with lower values. Um, so really, the main thing here, and we'll get into vorticity soon, the main thing here is that higher vorticity values are being brought into a area of low vorticity values. That is called PVA. Well, NVA is just the opposite, where low vorticity values are being brought into an area with high vorticity values. That's all that means. But that is very important to identify increased lift and just um, movement in the atmosphere, just overall. And then we have our lower atmosphere. This is around 10,000 feet. Um, very important to identify short waves, which is essentially um, kind of like an extra. Can't really find a way to explain it off top of my head right now, but it's like an extra source of energy. It's an extra source of lift, and usually they're associated with troughs. Usually they're found in troughs. Um, so when we identify these short waves, they can often increase the impact, the overall impact and the overall strength of a low pressure or an area of low pressure. Sometimes these short waves are really small, sometimes they're more expansive. So if we can pinpoint a short wave and maybe in an area of interest of severe weather, we can maybe say that could be an enhanced area to look at, or just an increased area of severe weather possible in that area. But also we can look at the depth of the and warm and cold air advection. So it's kind of the same process as the vorticity. warm air advection, you're bringing warm air into cold air, into colder air areas. So the same sort of thing, but we can see how much of that warm and cold air is being brought into an area. But that's the same thing as moisture advection, which is very important as well. To see how much moisture is being advected into your area, or how lack of thereof is being brought into an area. But also inversions are commonly seen on this level. Inversions are very important in severe weather forecasting because they can stabilize the air above the unstable air. And if you create the stable air layer above unstable air, it's a cap. It's like a lid, and you can't have those air parcels that are trying to rise because there's a stable air layer called an inversion trapping these air pollutants and air parcels and preventing them from rising. And you have to have rising air for thunderstorms. You have to have rising air just for in general for any sort of type of precipitation. You have to have rising air. But specifically thunderstorms, excuse me, you have to have rising air. If you don't have rising air, you're not going to have thunderstorms, and inversions will kill any sort of severe weather threat or thunderstorm threat if it's there strong enough. So quickly, we've mentioned this divergence and convergence. So just quickly, divergence is where horizontal winds flow out of an area. It causes air to rise and leads to clouds and rain and helps create low pressure centers. Convergence is the opposite. Horizontal winds flow into an area, causes air to sink. And when you have air sinking, that causes high pressure centers in clear weather. Like I said, when you have air rising, air parcels rising, you're going to have clouds and rain and low pressure centers forming. If you don't have those parcels rising and they're sinking, that's where we get the sunny weather and just the beautiful weather in general. So I mentioned this a little bit ago of how troughs are oriented and what does that mean and how does that make a difference? And I'm going to try my best to explain this. So a trough it looks like a U on a map, and I'll um, kind of kind of like this. This is a trough here. When we have this jet stream, the jet streak in like a U, looks like a U. That's your trough. And a ridge right here, you can see kind of the ridge back in here, kind of off the screen. Not really a great picture there. And, there's one right here, but a trough is like a U. But troughs bring your rainy weather, they bring your cold weather, they bring your low pressures. Ridges bring your high pressures. They bring your clear weather. They bring your just overall warmer, beautiful weather. Well, mainly here, what we're going to be focusing on are the troughs. That's what brings these severe weather systems in the first place. Well, there's two sort of oriented troughs that we look at. There's a positive oriented trough and a negative. Well, a positive is oriented southwest to northeast, pointing toward the northeast. This is not good for storms. This creates a weaker temperature gradient, and then that creates a just less chance for thunderstorms, and the low amount of turning the direction of the wind and the tilt of the wind will affect the shear and the turning of the wind. So, and I will explain that. Negative tilted troughs are oriented southeast to northwest. Great for storms. These bring stronger temperature gradients, which low pressures love, which also bring the greater chance of widespread thunderstorms. And this brings increased tilt, which increases the shear, which is very important for thunderstorms. So let me explain. Let me give you visual. Now, don't. Here's the link to the image where I got this from. But let's look at this. Let's look at these black solid lines here. And imagine in between these black solid lines, we have wind flowing parallel to these black lines. So they're following every curve, these black lines make these winds, right? Well, when we have a positively tilted trough, look at where our winds are pointing. They're pointing to our northeast, right? They're pointing to our northeast. Well, think about it. On our right, on the right side of a trough, almost always on the right side. So like, let's look at the negative tilted. This is a good example here. On the right side, first off, you can see the winds are oriented more north. Like if you look at the lines here, if you act like wind is going parallel, and between these lines, it's pointing straight north. That's allowing warm air on the right side of troughs. Warm air loves to rise into these low pressure centers on these troughs. And these low pressure centers love to sit kind of like on the right side of these troughs. So like right in here, you can see my cursor on the negative tilt. They like to sit right in here. And it loves to draw in warm air from the south. But you have to have the winds oriented in a way for it to do that. If you go in a positive tilted, look, the winds are east. They're pointing northeast. Well, that warm air isn't going to be drawn into this low pressure, which would be right around here. They're going to be pointed away, more towards away. So essentially, having a positive tilted trough leads to less likelihood of thunderstorms, and you're not getting that warm air and that warm, moist air drawn into that low pressure, feeding that low pressure system. When you have a negative tilted trough oriented pointing to the northwest, you allow that warm, moist air to really funnel into that low pressure, and you're going to get a better chance for thunderstorms. So when you're forecasting, when you're looking at maps, look at how these troughs are oriented, because that will determine if the system is going to be a high impact or not. So remember, negative tilted troughs when they're slanted to kind of the right here, that's usually a good sign for a lot of good moist air being brought in. Here's a picture of divergence and convergence. When you have convergence at the surface, it's like a counterclockwise movement. It's bringing air in toward the center in a counterclockwise fashion. And when you bring all this air in a centered location, it has to rise. So when you force this air to rise, you get clouds, and then you get divergence in the atmosphere because you get divergence in the atmosphere because when you're forcing something to rise, it's going to have to eventually spread out. It can't be forced to rise all the way up. It's going to have to spread out at some point. But vice versa, when you have divergence at the surface with the wind pointing away from each other um, in all directions, you're causing convergence in the atmosphere, air being funneled into this high pressure area of divergence. It's very interesting to think about. Um, Again, this picture does great. There's the link, and you could find more information about this on these links as well. Real quick, vorticity. It's essentially how much air is just being rotated in the horizontal plane. Um, you have the rotation of the Earth, you have the Coriolis effect, and then you have relative vorticity. All three kind of play a role in how air is being rotated in our atmosphere. That's all it really is. Vorticity is just air being rotated in our horizontal plane in the atmosphere, and it's caused by all sorts of things: the rotation of the Earth, and Coriolis effect as well plays a huge role. So it's very interesting.